Okay, so we're going to go ahead and start 4.4 today. And 4.4 deals with the topic of chain rule. And in my personal opinion, I think this section is the best predictor of long-term success when it comes to taking derivatives. This section is supremely important in this class. And if you want to be a good derivative taker, you have to understand this section really well. Like if you understand this section really well, no matter what type of function we take the derivative of, like later on in this chapter or later on in the school year when we get introduced to new types of functions, you're going to be able to take the derivatives of those functions. And if you struggle with chain rule, like taking derivatives moving forward is a really big problem. So what chain rule does is it's going to allow us to take the derivative of composite functions. And once we can take the derivative of composite functions, that allows us to take the derivative of much more complicated functions. So you guys are going to see that the functions that we're going to be looking at become a lot more difficult to differentiate and a lot more difficult to simplify as well. Okay, so what chain rule states is that if f and g are both differentiable and f composed with g is the composite function denoted by h of x, which is equal to f composed with g of x, then h is differentiable and given by the product below. Okay, so if we want to find the derivative of a composite function, the derivative of h is h prime. The way we take the derivative of a composite function is we're going to take f prime of g of x, and then we're going to multiply that by g prime of x. Okay, so when we take f prime of g of x, f prime is the derivative of the outer function. Of g of x means we are evaluating that at the inner function, and then we multiply that by g prime of x, which is the derivative of the inner function. And you guys have seen how like some stuff that we've done earlier in the year has shown up in chapter 4. Like if you think back to the difference quotient, like we used the difference quotient in section 4-1 when we looked at taking the derivative of functions using the definition of the derivative. Well, you guys are going to see something come into play right now with chain rule that we looked at earlier in the school year in chapter 1 as well. Okay, if you guys remember in section 1.4 on composite functions, we looked at like a function h of x where you had the function x squared plus 1 and you raised that to the 4th power, and we had to identify the inner and outer function in the composition. Okay, so when we look at this function here, the inner function in the composition was the function g of x, and looking at this, the inner function in the composition is x squared plus 1. The outer function in our composition was f of x, and the outer function in that composite function is x raised to the 4th power. Now, this is going to be the only time that I work the problem out like in this way. We're just going to get into like using the chain rule in the future, but just to look at this really quick, when I take the derivative of both of these functions, the derivative of g, which is g prime, is going to be 2x, and then the derivative of f, which is f prime, is going to be equal to 4x cubed. So if I want to take the derivative of that composite function, h prime of x, that is going to be equal to f prime, which is 4x cubed. We're going to evaluate that at the inner function, g of x, which is x squared plus 1. And then we're going to multiply that times g prime of x, which is 2x. And the only thing for me to do in simplifying this is to like rearrange the order of the factors. So we can make h prime of x equal to 8x times x squared plus 1 cubed. Okay, and that right there is the derivative of that composite function using chain rule. Okay, so we're going to do like a couple of like basic straightforward chain rule examples just to give us kind of practice in using chain rule to take the derivative of a function. And then the last example we'll look at will kind of lead us into Friday's lesson, where we're going to look at like a more complicated problem involving chain rule. Okay, so the directions for these examples ask us to find the derivative. For number 1, we have f of x equal to the quantity 2x to the 4th power plus 3x plus 1, which we are raising to the 8th power. Okay, so pretty obvious looking at that is a composite function. So if we're going to take the derivative of this using chain rule, the outer function in the composition is x to the 8th power. The derivative of that is 8x to the 7th power. We're going to evaluate that at the inner function. So the inner function is 2x to the 4th plus 3x plus 1. And then we're going to multiply that by the derivative of the inner function. So the derivative of 2x to the 4th plus 3x plus 1 is going to be 8x cubed plus 3. And we're not going to multiply this out because the factored form is the most simplified form for our derivative. So again, I'm just going to rearrange the factors where I can rewrite this as 8 times 8x cubed plus 3 times 2x to the 4th plus 3x plus 1 raised to the 7th power. Okay, and that right there is our derivative simplified completely. Okay, so for the last 3 examples that I'm going to work out for you guys, I want you to pause the video so you work the example out on your own, and then when you have it completed, unpause the video, and then you guys can like follow along as we work it through together. Okay, so taking a look at number 2, we have the function g of x equal to the cube root of x squared plus 3. So I know that I can write this function as x squared plus 3 raised to the 1/3 power. I want us to get to a point where we don't have to use this step or do this step when taking the derivative of a radical. Okay, you guys by now should know that cube root means some quantity raised to the 1/3 power. Okay, so if we're going to take the derivative of this composite function using chain rule, the outer function in my composition is x to the 1/3, whose derivative is 1/3 x to the negative 2/3 power. We're going to evaluate that at the inner function x squared plus 3, and then we're going to multiply that by the derivative of the inner function, which is 2x. Okay, so we just want to go through and simplify this expression by rewriting it in the form of a fraction and a radical. So when I multiply all that stuff together, the only factors that we're going to have in the numerator are 2 and x. In our denominator, we have a factor of 3, and then x squared plus 3 to the negative 2/3 power is going to put x squared plus 3 to the 2/3 power in our denominator, which is going to be the cube root of x squared plus 3 quantity squared. Okay, and that right there is our derivative simplified completely. Okay, you guys give number 3 a try. So for number 3, you have the function f of x equal to the square root of x cubed plus 2x plus 8. Okay, so that function is equivalent to x cubed plus 2x plus 8 to the 1/2 power. Again, we have a composite function, so we're going to use chain rule to take its derivative. The outer function in the composition is x to the 1/2 power, whose derivative is 1/2 x to the negative 1/2 power. We're going to evaluate that at the inner function, x cubed plus 2x plus 8. And then we're going to multiply that by the derivative of the inner function, which is 3x squared plus 2. Again, when I write that in fraction and radical form, all we have in the numerator is 3x squared plus 2. Our denominator is going to have a factor of 2 and also a factor of rad x cubed plus 2x plus 8. Okay, so that right there is our derivative simplified completely. All right, so for number 4, you have the function g of x equal to x to the 4th power times the quantity 3x minus 2 cubed. Okay, so this one's a little bit different in that the rule that we have to use to start taking the derivative of this function is product rule, because we have the product of two functions, x to the 4th power and then 3x minus 2 quantity cubed. So if we're going to take this derivative using product rule, this is going to be the only example where I work this step out, okay? But if we're going to use product rule, that's going to be the derivative of the first function. So I'm going to use d over dx to represent the derivative. So we're going to take the derivative of the first function, x to the 4th, times the second function, 3x minus 2 cubed, plus the first function, x to the 4th, times the derivative of 3x minus 2 cubed. Okay, so that's using product rule. Now, let's go ahead and take the derivative here. So the derivative of x to the 4th is 4x cubed times 3x minus 2 cubed plus x to the 4th times. Now, if we want to take the derivative of 3x minus 2 cubed, we have a composite function, so I have to use chain rule to take the derivative of that function. So, like, this problem is a product rule problem, but embedded in product rule, we have to use chain rule to take the derivative of the second function. Okay, so if I want to take the derivative of that second function, the outer function in the composition is x cubed, whose derivative is 3x squared. We're going to evaluate that at the inner function, 3x minus 2, and then we're going to multiply that by the derivative of the inner function, which is 3. And that's it as far as the calculus goes for this problem. Again, that derivative is a little bit more complicated than what we've done up to this point, but still the tough part with this problem is the algebra involved in simplifying the derivative. So let's go ahead and work through that next. So when we look at these two quantities here, this one and this one, how many different factors, different types of factors do you see when you look at those two quantities? And for me, the answer is there are 3 different types of factors. Okay, we have a numeric factor. So when I look at those two quantities, the numeric factors are 4 and 3 times 3, which is 9. There is no like greatest common factor that we can factor out of both of those numbers. Okay, when I look at the next factor that both quantities share, it's x raised to some power. So when we look at our two factors of x, we have x cubed and x to the 4th. What is the greatest common factor of those two quantities? Well, it is x cubed. And then our last type of factor for this is 3x minus 2 raised to some power. So when we look at 3x minus 2 cubed and 3x minus 2 squared, the greatest common factor of those two quantities is 3x minus 2 quantity squared. Okay, so when we factor that out from both expressions, when I look at this first quantity over here, what are the leftover factors whenever we factor out x cubed and 3x minus 2 squared? Well, we have a factor of 4, and we also have a factor left over of 3x minus 2. Okay, when we do the same thing for this over here, when I factor out x cubed and 3x minus 2 squared, what are my leftover factors? We have a positive 9 and a factor of x. Okay, so all I need to do now is simplify the expression that I have in the brackets. Okay, so we get g prime of x here equal to x cubed times the quantity 3x minus 2 squared. When I distribute 4 across both terms, we get 12x minus 8 plus 9x. And then I can go ahead and combine like terms in the parentheses. So we get x cubed times 3x minus 2 squared. 12x plus 9x is 21x minus 8. And then when we look at 21x minus 8, is there a factor that both 21 and 8 share? And the answer is no, aside from the number 1, because the factors of 21 are 1, 3, 7, and 21. The factors of 8 are 1, 2, 4, and 8. The only factor shared between those two numbers is the number 1. Okay, so this right here is our derivative simplified completely because I have that derivative written as a product or quotient of factors. And I think this example is most similar to the types of examples that you guys are going to see in class next time. Okay, so you're going to be having to work with like power rule and product rule and quotient rule and chain rule simultaneously, and figuring out like in what order do you need to utilize those rules to take the derivative of your function. Okay, so we'll stop there for today and pick up from this point in class next time. Have a great day, guys.